In this session, we want to talk about planes. What is a plane? Can you see here? A piece of a white paper like this is a good example of a plane. But what's important about a plane that you want to note is a plane extends infinitely to the left, infinitely up, infinitely down, and infinitely to the left. It goes on infinitely. On the board, I made an attempt to draw a plane like this, like a parallelogram. In a three-dimensional space, how can you uniquely identify a plane? To do that, you need at least 3 points on the plane, such as 1, 2, 3. With 3 points on the plane, you can uniquely identify a plane in a three-dimensional space. I have called this point A. I didn't name these two other points, alright? I just named this point A. And for this point A on the plane, it has a position vector OA. Now, when I say the position vector OA, I meant this. On this plane, right? On this plane, the point A maybe sits here. Right, the point A sits here. The point A sits here. When I say the position vector of the point A, you have to imagine it correctly. This is the point A, the origin is probably beneath it. So this green stick, okay, can you see it's green color? Let me show it again. Alright, can you see? This green color stick represents the position vector of the point OA here. OA. Just that you must imagine it like this now. It's like this. Right. This is the position vector of the point OA. Let me call this vector just A. I did not name this point, nor did I name this point. But allow me to call this vector B. If I know these 2 points, I can always find this vector, right? By taking the position vector minus the other vector, I get OB. And likewise, I want to name this vector as C. Okay? So on this plane, I have named only 1 point as A. I named this vector as B and C. I didn't name these 2 points, alright? It's okay. Alright? So with 3 points, I can always define a plane in a 3-dimensional space. For the first point, the position vector, which is OA, right, is drawn like this. And then now I have the vector B and the vector C lying on the plane. We are interested to actually write down an equation for this plane. An equation on this plane means an equation that says something about the general point on the plane. General point on the plane means a point that's marked anywhere. Say maybe I mark my general point on the plane as the point here. Okay? The vector of the point R, it has a position vector. Once again, you must get this perspective correct. When I draw the vector OR like this, I meant to say, if this is my point A, my R is, say, somewhere here. When I say the vector OR, right, this is a plane, right? OR, I meant the vector like that. So you must get your perspective correct, okay? This is the vector OR, from origin O to the point on R, OR. So our attempt here is to try to write down an equation that say something about the vector OR. Looking at this diagram, I can see that the vector OR is equals to OA plus AR. Okay, I want you to notice that this vector OR, right? OR or simply R. Let me adjust R again. Okay, this vector OR is equals to OA plus AR. Where is the vector AR? Let me draw for you on the board. This is the vector AR. So for this generic point R, the position vector OR or just R is equals to A plus the rate vector. And now we want to make an attempt to find this rate vector. Let me erase off this because it's a bit cluttered. Okay, now to find the vector AR, I want to complete this diagram, this parallelogram here. I hope my diagram is good. Okay, so now to find the vector AR, right? To find vector AR, I can see that this vector AR can be found by taking this vector, which is a multiple of B, plus this vector, which is the same as this, and so it's a multiple of C. Once again, this vector AR can be found by taking a multiple of B. You can see this is a multiple of B, right? From here to here, a multiple of B plus this vector, and this vector is actually a multiple of C. So now I can replace it as, okay, somehow the okay, let me do this. I find this one not straight enough. Okay, okay, it's better. Okay, now, so I'm going to write this vector AR as a multiple of B plus a multiple of C. Okay, so once again, AR, a multiple of B plus this, and this is a multiple of C. And lo and behold, you have what is called an equation of a plane. And what do you notice about this equation? It's made up of three vectors. This first vector is the position vector of a point on the plane. When I say this, I meant this first vector, right, must be a vector that's like this, OA. Secondly, a multiple of B. B is a vector that is, can you see? B is a vector that is parallel to the plane. So B is something like this. Okay? B is something like this. And then C is another vector that is parallel to the plane. So what I have here is A represents, okay, A, right? This A represents the position vector of a point on the plane. Right? How about B and C? B and C, they are just vectors parallel. They're just vector parallel to the plane. Now, what's important to note is it can be quite misleading to think that that this vector B and this vector C, right? You tend to think that those two vectors must be so-called like that, no, on the plane, no, it need not be, no, it need not be. B and C are just free vector. They are just vector parallel to the plane will do actually, right? And another thing you have to note is, important note is, B and C are not parallel. Not parallel to each other. I hope you can see. Right? Okay. So these two vectors represents vectors that are parallel to the plane. B is parallel to the plane and C is also parallel to the plane. The important thing to note is these two vectors, right, mutually they cannot be parallel to each other. Right? They must be two non-parallel vectors to the plane. B and C are just two vectors. Mutually they are not parallel to each other, but they are parallel to the plane. And this is the equation of the plane. Where lambda and mu, they are just numbers. Okay, we write properly. Alright, that gives us the first equation of a plane in vector form.